So let's get started. Good morning again, or afternoon or evening, it depends on where you are. I'm Patrizia Rossi. I'm the chair of this committee for the ISNAF Young Investigator Bruno Touschek Award. Just let me say a few words about ISNAF. ISNAF is a non-profit organization whose mission is to connect, empower, and celebrate the Italian intellectual diaspora in North America. It connects more than 3,000 scholars, researchers, and technologists in North America, as I said. It was established in 2007 by 36 prominent Italian scientists and scholars, and among these, 4 people who, 4 Nobel Prize recipients. As I said, ISNAF promotes networking and cultural, scientific, and academic, technological cooperation, and is honored and proud to be under the high patronage of the President of the Italian Republic. This is a really big award, let's say. Let me say now a few words about the Bruno Touschek Award. It is a quite new award because it was established only 2 years ago. This is the 2nd year, and it was established in 2022 by the Istituto Nazionale di Fisica Nucleare. And this award honors, as the name said, the memory of Professor Bruno Touschek for his pioneering work in the field of elementary particle physics, and also accelerators, and it recognizes prominent contribution in the field not only of fundamental particles and nuclear physics, but also astroparticle, as you can see from the finalists of this competition. So as I said, this just to introduce who we are, what we are doing here today. And let me introduce my colleagues who we work together for the selection of the, let's say, many very good, also excellent applications that we received this year. So Professor Elena Orlando, she's Associate Professor at the University of Trieste, and Dr. Alessandro Ratti, who is also the co-chair of this committee. He's a deputy for Accelerator Technology and the Engineering Division at the Lawrence Berkeley National Lab. And with that, I think that we can, after this introduction, I think that we can start with the presentations. As you know, we have 3 finalists. Each finalist has 15 minutes for her presentation. And then we have 8 minutes for a question and answer. And at the end, we will have the final remarks. So let's start with, as we said, with Simone Mazza. And Simone, we talk about, Simone is an assistant project scientist at the University of California, Santa Cruz. He will tell us about the critical detector development for high energy and nuclear physics. Simone, you have 15 minutes and you can start.
All right. Yeah, thanks a lot for the introduction. So just a very brief correction. So now I'm an assistant research scientist, so I'm a full PI. And this happened in September, so that's why in the application it was actually different. And I am at SCIP, Santa Cruz Institute for Particle Physics at the University of California, Santa Cruz. And I work on a lot of projects, but my main line is the development of ultra-fast silicon sensor and also diamond sensor in a little bit, R&D for many projects. So to start, I want to give a controversial statement, which is the current HEP research is at a standstill because we did discover the boson, the Higgs boson at LHC. So we know that the standard model is complete. But we also know that something is out there because we do have several contradicting observations like hierarchy problem, dark matter and energy, matter-antimatter asymmetry. So we know that there is something out there, but we still don't know for sure how to search for it. The upcoming big experiment is going to be high luminosity LHC. However, we don't really foresee a big discovery there because mostly we're going to look for Higgs in muon decay and Higgs production. So there is really nothing to search for. Well, we are kind of entering an era of experimental-driven discovery. And I think the immediate need is a series of small-scale experiments to stand little bits of the standard model. So I'm going to talk about the Pioneer experiment, which tests the lepton flavor universality violation. Then we want to study the nucleus structure at the electron-ion collider, which is also a great stepping stone for technological development. And in the far future, we are going to have the next generation of collider, like the X factory of 100 TeV Hadron Collider. And a thread that connects all of these is the development of enabling technology. So I want to start with high-lumi LHC. That was my first work here at SCIP. We do ramp up the intensity for high-lumi LHC, so we need to mitigate the pileup. And to do so, we thought about 4D tracking, so using timing in tracking and assigning a time for each hit in the tracking process. To do so, we want to use low-gain avalanche detector, or LGAD in short, which is initially a blue sky R&D initiated in early 50. These are thin silicon detector with gain and can get to 20 picosecond of time resolution. The LGAD development started in 2012, but already in 2019 and 20, Atlas and CMS submitted TDRs for large-scale timing upgrades, and it was the main editor for the Atlas timing layer. In here, the radiation hardness challenge was the big one, so we wanted to get to 2.5 10 to the 15 fluence, and there was an extraordinary development in a few years to get to that level. But there are still a few big issues, like the low granularity of LGADs and the high power dissipation of the electronic, and also going to extreme fluence. So to solve the low granularity issue and also the power dissipation, we thought about AC coupled LGADs, which is actually a patent here at UCSC, where we do have a continuous multiplication layer with a resistive M+ layer and AC coupled readout. So the collected charge is shared between pads, and we can have a position resolution that is much better than the pitch. So the new concept of a tracker is to have a sparse readout but high precision, and this, thanks to sparse readout, we also have low power. And the upcoming AC LGAD application are the electron-ion collider in the EPIC detector and the Pioneer experiment. And next, we foresee FCCE. I'm currently waiting for a grant together with BNL for machine learning reconstruction in this kind of detector in AC LGAD using hardware acceleration. And then if you look into the future, we actually need a much higher radiation hardness requirement, so a few order of magnitude, and we also need to go to higher occupancy, especially if in FCC-HH or in the muon collider. So there is a critical need to continue developing LGAD sensor technology for this application, and here you can see kind of a snapshot of how we want to go for high granularity and how we want to go for radiation hardness. And I'm personally one of the inventor of the deep junction LGAD that you can see schematics here. We did produce the first prototype with SPIR phase 1 and 2 grants. I just secured a grant for a DJ LGAD fabrication with FBK in Italy through the RD50 collaboration. And I'm currently waiting for a DOE grant for DJ LGAD fabrication at BNL. And in this case, it's also combined with black silicon technology for DUV detection. So for the future experiment, Pioneer, as I was saying, is a great experiment that I'm one of the leader of, and is a next generation rare pion decay experiment that is going to happen at PSI. In the phase 1, we want to measure the charged lepton flavor universality, or mu, and measure it with a precision that is 10 times better than what we have now, so that we can have a number that is comparable with the theory calculation. And then in phase 2 and 3, we want a precise measurement of the pion beta decay branch infection, which is important to test the CKM unitarity. In the last year, Pioneer was officially formed as a collaboration, and we are now seeking major funding. There are 3 main detectors: the ATAR, which is the active target, a tracker in between, and then a calorimeter that is either liquid thinner or LISO with very good energy resolution. As I was saying, I'm leading the design of the active target. So I developed the sensor, readout, digitizer, other components by working with other university group and with companies. I'm also mentoring a PhD student to develop the simulation framework for Pioneer and optimize its design. And I'm also co-supervisor of a PhD student in Zurich. So the chosen technology for this active target is a high granularity LGAT detector because we want high signal to noise, full fast collection time, and great time resolution. Currently, I'm waiting for a DOE grant for the ATAR development, and we are planning to submit soon to an NSF mid-scale development grant to be the first demonstrator. So the ATAR is a 2x2 centimeter wide, 16 millimeter thick block of silicon tracker with high granularity and high position energy and time resolution, because the two decays that we want to measure is pi nu and pi mu nu. And the two decays are actually well separated in energy. However, there is a tail here that we cannot see in the calorimeter, and that's why we want to use the ATAR. Basically, in the ATAR, you will see these decays live, and you will be able to tell if the pion first stopped and then went to a muon or went directly to an electron, and all the in-between cases where the particle decay in flight. So now the PhD student I'm working with has implemented a BDT pion decay in flight event suppression, and now is working on the design optimization. Then switching on to the electron-ion collider, the AC will provide some key measurement like the proton spin, the motion of quarks and gluons in the proton, provide tomographic images of the proton, and study the QCD matter at extreme gluon density. For the EPIC detector, we foresee a barrel and end-cap time-of-flight layer based on AC LGATs. For the barrel, we want strips. For the end-cap, we want pixels. And we are also very stringent in terms of material budget. We want something like 25 to 35 picoseconds single hit time resolution and a 30 micron spatial resolution. And we want that because we want to do PID with time of flight. So this happens up to a few GeV, and we can separate between electron, pion, kaons, and protons. Currently, I'm sensor coordinator for the EPIC TOF detector. We just finished working on the PDR. So I work on the development of AC LGATs. I organize the irradiation campaign and the sensor testing. We were granted here at SKIP an engineering grant for state demonstrator from JLab, and also R&D funds for the last 2 years, and I'm waiting for the next round. We are also considering applying for a major grant for R&D for AC detector too. And in the future, I'm thinking of being involved also in the simulation and in the data analysis by dedicating a PhD student to EPIC and possibly apply for a base grant. I'm sorry. Then the other challenge here is the readout. So the sensor can give you 20 picoseconds, but you have to maintain it in the readout. And the power consumption is a big issue. So we need, for a low jitter, low power, so less than 1 milliwatt per channel chip. For AC LGAT, we are kind of already there, but when we look at the future for higher density environment, it's going to be an even bigger challenge. So at SKIP, I've been working to develop 3 different chips, one with INFN, another 2 with companies here in the US through SBIR. One is FAST with INFN Torino, one is HPSOC with Nalu Scientific, and one in the ASRock with Anodyne. The most advanced one that we have is HPSOC, which has a fast amplification and an integrated 10 gigasample ADC. You can see here some picture of the chip, some results using a strip AC LGATs and some pulses out of the chip. And at the moment, I just submitted another SBIR for a LGAT integrated readout or lead with Nalu.
We have 5 minutes left. 5 minutes left.
And if we look more into the future, there is the IDEA detector for the FCC-EE. And in there, we want to have a silicon wrapper that has actually a very large area, more than 60 square meters. So it's really huge, considering that until now, we only had timing layers of the order of 10 square meters. So to not explode the number of channels with this such large detector, we want to still use AC LGATs. And in this case, again, the occupancy is not an issue, so we can freely use them. And the high timing precision is also needed for time-of-flight PID and long-lived particle detection. So at the moment, I'm getting involved in the US FCC effort for the silicon wrapper, and I'm working with an undergrad here at UCSC and other faculties to implement the AC LGAT response in the simulation framework. And the geometry for the barrel is strips. So very similar to EPIC and what we are doing now. And then if we look beyond HEP and nuclear physics, we can use this alga detector. This is a project that I've been working on for a few years at SLAC SSRL, looking at the fast repetition rate of the cyclotron. So we can clearly see 2 nanosecond beam separation. As you can see in this plot here, this is the response of the sensor. We have good linearity with X-ray energy, good time resolution of less than 10%, and good time resolution of around 100 picoseconds. We also tested sensor with a focus beam there at SSRL, and you can see here the response of an AC alga strip detector to a beam as it crosses over the detector. And then another kind of last 6 months interest that I had, but that might grow substantially in the next few years, is nuclear fusion. There is a UC organized workshop in December of fusion, and that could be the start of a UC-wide effort. And we want to try and apply alga technology and also diamond detector to plasma monitoring in fusion. We are kind of growing the expertise of diamond detector here at SKIP. Is mostly the work of another faculty for now, but have been increasingly involved in the last year or so. And depending on the fusion technology, whether you want to use Z-pinch or inertial confinement, you want to use either of the two technologies. For example, for inertial confinement, diamond will be really good because it's really radiation hard and can be very close to the fusion events. And then using thin detector, either silicon or diamond, is good for high repetition rate and low mass angle detection. And here is a picture of me visiting NIF to actually kind of try to understand what are they need in terms of sensor development. So to go into the conclusion, there are kind of dull but interesting time ahead because the breakdown can be unexpected. As a community and also personally, is a great time to look ahead. And one crucial enabling technology is for the tracking and timing that is kind of cross-cutting across a lot of different fields. The first application will be the Atlas and CMS timing layer on high Lumia Lake C, but next we already foresee Pioneer, EPIC, and in the far future also in FCC-EE. There are many challenges that lie ahead in terms of precise 4D tracking. At the moment, we're kind of exploiting this AC alga workaround, but when we go to high pileup, it's going to be even harder, both in terms of granularity and in terms of power dissipation. So we really need to have a technology development aimed at future colliders. But my point is that there was a great and fast development of 4D detector based on the alga technology in the past few years, and this is really a good technology for short, medium, and long-term application. And then there are also diamond and high band gap material like silicon carbide that are further into the horizon. The timing technology is also an interesting technology for photon science, medical science, and possibly nuclear fusion. So this is really cross-cutting. And this is my last slide. Thanks a lot for the attention.
Thank you very much. And Simone, and I think that we can start with the questions. Who wants to start? Alessandro? Do you have a question, Elena?
Yeah, so thank you for Simone for the very detailed presentation. And what would you say if you had to summarize your main research in a couple of minutes to a less experienced audience, like explaining why it is important and your contribution on it?
Well, so what I do mostly is sensor development. I also do a little bit of physics, but mostly I do sensor development. And as I said, this is really cross-cutting. So I did sensor development for the Atlas detector and did a lot of testing, organized the radiation campaign. And this is really important because once you go to high luminosity, when you have a lot more particles flying by, you really need this 4D tracking trick, where this is a nice example where you have a bunch of hits in your tracker and it's hard to actually see one track from the next. But then if you assign a time to to each one of these hits, you can say, okay, this track, it's all at the same time, so we know that it's one track and it's separated for this other track that happens at another time. And then with this technology, we are now developing, as I said, AC algorithms, deep junction algorithm, and a lot of other technologies, and each one has a different specific application. And this is, again, important for HEP, like in the case of the Atlas detector for Pioneer AC, but it's also can give technological advancement in other fields, like in medical science, in space. There is talks of using algorithms in space for tracking because they can tell you whether a particle is coming from one direction or the other. And as I was mentioning also in photon science, because they can give you this fast repetition rate and still look at low energy X-rays with the convenience of silicon detector that is not immediate if you go to 1 or 2 keV X-rays. And also nuclear fusion. I mean, that this kind of technology development is very important for a lot of fields.
Thank you.
A couple of questions, if Alessandro, please.
Okay, the one question I had is in particular in large physical experiments, the signal count is very high. I know you work with just the sensor part, but how hard is it to integrate a very high density into a full readout system?
So
meaning how does the high volume of channels impact your detector development, as well as how does that integrate then in the rest of the experiment?
Well, the detector are coupled in some way, so with some kind of integration that can be wire bonds, bond bond, etc., to a readout chip. Usually this readout chip sits on, let's say, a flex or a PCB. And in case of a large timing layer like the Atlas high granularity timing detector, what we do is there is a clock distributed on all the chips, and then the chips there have their own TDC, so they can return back your time. So you do ship back all this information in digital form usually. So it's kind of serialized into digital communication from the chips to the front end. And usually all of these channels go into a backend crate where the data is either stored or used directly for trigger assessment. And one big issue, as I was saying, for large detector is the channel count. That's why we want to use AC algorithm in so many projects, because it simplifies the readout by reducing the channel count. And another big issue is that when you have timing information, you need a high power amplifier to get to the frequency needs to get good timing, and that's why we want to sparsify the readout, at least for until FCCE we can survive with that.
We have time for a last short question.
Yes, because it's a little bit a follow-up of what Alessandro asked. Me too, I had a question about the readout, to understand with all these channels, how do you then reconstruct with your events? Because at the end, you are interested in the event, right?
Yeah.
Are you using a streaming readout? Because for EPIC, I know that there are the goal is to use a streaming readout, but then in your explanation to Alessandro, you said about kind of trigger. So I'm trying to understand if this is, let's say, the full readout and the reconstruction of the event is still under development and you are just doing some tests. I'm trying to assess at which level is your study. Because if you test just one a small sample, then what it comes after the signal is a simple chain. But if you want to read out all detectors or the full events, then it's another question. So maybe you don't have time to elaborate the response for my question, but I'm quite interested in understanding this part. I think it's a simple problem.
It depends a little on the type of detector, right? For APIC, I'm not fully involved in the other part of the detector, but for the top layer, we do have a traditional readout chip. I don't know if it's a streaming readout. I don't think so. For the top layer. I mean, we do have two different chips, one for the barrel and one for the end cap. The issue is that they're very late with the development, so I haven't seen a lot of results from the readout chip, and I hope that will happen in the next year or two. But yeah, unfortunately, we don't have a readout that is completely designed right now for the AC algorithms.
May I ask a very short question to make a better assessment of your work, Simone? So you presented a lot of projects, big projects, Pioneer, Atlas, LHC high luminosity, FCC even at the end. So, and you have a postdoc here and there. So how much these projects overlap each other in order for you to be able to follow, and which is the percentage that you dedicate to your work, to this project?
Well, the answer is that since I do a lot of sensor development for a lot of these projects, it's really connected together. Like the AC algorithms that I'm developing for the electron ion collider, they're also interesting for Pioneer, and they're also interesting for FCCE. And same thing for the readout. So for the electron ion collider, I'm working on mostly HPSOC, and FAST that was of relevance for the electron ion collider is now also very relevant for Pioneer. So in a sense, I try to keep myself developing the technology and how to apply to the different projects. That's why I'm also doing all these projects for fusion and for X-rays, because I know the technology and I know how to respond to different excitation. And so it's the sensor that I test at SSRL are the same that I test for Pioneer.
So maybe say that 80% is more or less the overlap, just to have a feeling.
Like 60%.
60%, fair enough. Thank you very much. It seems that I have to rush because we have a limited time. Thank you very much, Simone, for your very clear presentation. And then we move to the second candidate, is Dr. Luigi Marchese. Is a junior distinguished researcher at Fermilab. I don't know, Luigi, if you also changed your status in the meantime. And you are going to talk about seeing the invisible with the creativity in high energy collisions. Please.
Yes, can you hear me?
Yes.
Okay, I'm going to full screen mode. Okay, and I start. If you can see it, I start.
Yeah.
Okay, so thank you for being here and having the opportunity to give an overview on my research in the past years. In this talk, I will try to give you an idea of how somehow sometimes you can overcome experimental limitation with creativity in high energy collisions. So a few words about me. I'm originally from a small village in Italy, Cervinara, and then I studied in Naples. But then I moved to Caltech for a first research on gravitational waves. And after that, I moved to Fermilab and Bologna, moving to high energy physics, working on the CDF experiment. And then I moved back to Europe, working on the Atlas experiment at the University of Oxford, where I got my PhD. And later, as a postdoc, I moved to ETH Zurich, and this time on the CMS experiment. And now I'm back on this side of the ocean, working still on the CMS experiment at the Fermilab Large Hadron Collider Physics Center as a junior distinguished researcher. To reply to your question, Patrizia, I'm still with this position. I actually recently was recently told that I got a second grant to continue my research at the center. So sometimes when I think back to the past 10, 15 years, it really feels a bit like being a tennis ball over the Atlantic Ocean. So many places, but there is a common denominator, a big passion for research in physics. If I had to think about a starting line for my research in high energy physics in the past 10, 15 years, I would say the best would be, we know this cannot be measured. And how we proved that this was wrong. For a reason or for another, every time I joined a different experiment, I had the opportunity to work on something that was considered not possible. And then we tried with creativity to prove that this was wrong. And this is what I'm going to tell you here with these, with a few examples. So all these international flights and traveling means also domestic traveling at the LHC. Our first stop in this talk is the Atlas experiment, where I worked on the Higgs boson. As we know, this is a really important particle responsible for giving mass to fundamental constituents of the known universe. It was long searched, and after 12 years of research, we had amazing results. But there are, and the Nobel Prize, of course, but there are some important results that are still waiting for a better measurement. So, how do we produce the Higgs boson at the LHC? I don't want to be technical, I just want to give you the full overview, but I ask you to focus on the leading production mechanism that is initiated by a pair of gluons, because this will be back on my talk. And what I want to make here as a point is that if we consider the real numbers of how many Higgs bosons we did produce at the LHC in 2015-2018, what we call run-2 data taking campaign, well, we produced for every inverse femtobarn of data 55,000, but we only detected 170. This is just to tell you how challenging it is. So that's about the production, but this is not how we do observe it in the detector. The Higgs boson decays quickly, and there is a big variety of decays, and I want you to focus on this specific one, a pair of Z bosons. So, as we know from quantum mechanics, when a particle decays to many possible other particles, you can define a partial width, which is basically telling you, together with the branching ratio, the total number of times the particle decays to these specific particles out of the total possible decays of the particle. And so, if you sum up all the possible partial widths, you are left with the global information. Why this is so important? Because if you measure all the expected decays to standard model particles, what we call visible, and you measure independently the Higgs boson total width, if everything does match with this equation, well, that's a clear indication of new physics, maybe decays to dark matter candidates. And this is a portal to new physics. So the point here is that that's really hard, because the standard model expectation for this parameter is 4 MV, but the best we can do with the LHC resolution is 1 GV, and we even tried at Atlas, and you can see the result with this straightforward road, as this road ahead, it was more or less at this order of magnitude. So many physicists believe that this was not possible at the LHC. However, think about, there is possibly a way I go back to the production initiated by two gluons and then a decay to a final state. As we know from quantum mechanics, in the end, this production cross-section just depends on couplings to initial state particles and final state particles and the Higgs boson total width. However, we know that thanks to Heisenberg uncertainty principle, it is possible to produce an off-shell Higgs boson. Off-shell means that this Higgs boson is not at the right mass. It is a virtual particle, and as such, the production cross-section doesn't depend on the total width, but just on couplings. So if you make a measurement of the ratio of the off-shell to the on-shell production cross-section, off-shell, on-shell, you can indirectly constrain the Higgs boson total width as this curvy road. So this is a brilliant idea, but however, the width is really narrow. As we know, the Higgs is a narrow peak, and so it's more like that. So there is basically just few events. However, it was studied that if you study a specific final state, a decay to Z bosons, well, then there is an enhancement here in the production cross-section. And there is even a cool name. A theorist, Giampiero Passarino, called this a camel-shaped mass line. You know, I was so surprised that I was going to find physics in a camel hump, but there was so much physics. And this is the real plot from the paper, which you can see here. So, of course, this needed to be observed, and this is what I did at the Atlas experiment. This required a lot of interaction with theorists, and here you can see in the ZZ channel the enhancement that I did observe in the work I did, and this was the measurement I performed for the Higgs boson, so it was less than 14.4 MV. I want to just remind you the comparison with the direct strategy, this is an improvement by a factor of 40, and this was the most precise result in 2018 for a parameter which was supposed not to be measured. And now this is superseded by a new measurement from Atlas with more statistics and more precise. So then we move along the LHC ring, and then when I joined CMS, I got interested in another research topic that was puzzling the physics community. As we know, in the standard model of particle physics, there are three fundamental charged particles, electron, muons, and taus, collectively known as leptons. So while in the standard model, they are known to interact differently with the Higgs boson, explaining their very different masses. It is also true that in the same model, they are expected to behave identically when participating in electroweak interaction. This is a symmetry known as lepton-Flavor universality. So we proved this with decades of measurements since the 60s. However, it is a few years, 12 years since 2012, that 15 measurements from very different experiments are casting doubts on LFU, lepton-Flavor universality, for the heaviest tau lepton. And, you know, more or less, all of them are about studies of B meson decays, particles containing a B quark. The global indication is that we reach for this tau anomaly a significance of 3 sigma. As we know in particle physics, to be able to claim for an observation of new physics, you need to have at least 5 sigma. So this is significant, but is still not yet to claim able to claim a discovery in particle physics. So when in 2012,
5 minutes left.
When in 2012, when many physicists wondered if it was possible to contribute at CMS, and many of them thought that this was impossible because, I mean, we are not like the LHCb experiment that is specifically designed to study B physics. However, with a smart idea, you can make this possible. So follow my reasoning. If you basically study the decay of a meson, like the B sub C that decays to a shape psi and the tau lepton, and then the same process just with a muon, and you can see it here, since you study a ratio of the two, basically you cancel out common systematic uncertainties, and this can become a sensitive LFUV probe, because then you compare this with the expectation you have from the standard model of particle physics, and deviation from these are an ambiguous indication of new physics. The impact of this would be tremendous because you would change the symmetry architecture of the standard model, and experimentally we are now thinking about the post-LHC machine, like the future circular collider. If we know that there is new physics, this could set a clear benchmark for the physics program of these machines. So no wonder that you can quantify the impact in terms of papers and people attending workshops on this topic, and this is huge. So how can we do this at the CMS experiment? First, we study B sub C because this is strategically good. This is the only place where you can produce them. It is the LHC. So this is a unique opportunity for CMS and the LHCb. And there is just one measurement from LHCb. But how can we be competitive at CMS? And here comes the creativity part. If you study decays of J psi to mu mu and muon decays of a tau lepton to muons, well, look here, in the numerator and denominator, in the final state, you just have muons and neutrinos. And the compact muon solenoid is excellent at identifying and reconstructing them. So this is key for a precision measurement, and this is the key to allow CMS compete here. So this is what I'm showing you here, that we did it, and you can see how tough and challenging it was to select especially the rare tau signal here, the numerator, compared to the other processes. This is taken from the latest paper I worked on, and here you can see the final result. So the starting point for this transition was 3 sigma. This is the first result of this kind at CMS, and is the first that is breaking this trend of deviations because it is consistent with the standard model within 1 sigma. So while this proved that CMS can compete, however, this is not the end of the story because we now need more precise measurement to completely rule out new physics. So a lot of these physics results cover for technical work. I was super lucky because every time I joined a different experiment, I had the opportunity to join different sub-detectors. So at Atlas, I worked on the inner detector and the muon spectrometer, and my work on the muon momentum reconstruction allowed Atlas to perform another high precision measurement, the most precise measurement of the Higgs boson mass. And there was a lot of work on the detector disalignments, as you can see here, a careful understanding. And there were a lot of night shifts in the Atlas control room, first as inner detector shifter, and later after getting some experience as a shift leader responsible for the whole crew and data taking. Here you can see around Christmas, we were celebrating the last day of round 2 data. So then at CMS, I became a light hunter. I joined the effort for the electromagnetic calorimeter and its beautiful 75,000 lead tungsten crystals. The system able to monitor their safety is a record system with more than 100,000 monitoring parameters. And here you can see I was the coordinator of the group when we had to upgrade everything during the pandemic. Here you can see a photo from the cavern. That was really a challenge. And now at CMS, still at Fermilab, I work on the upgrade of the tracker detector to be sure that CMS can perform high quality results even at high luminosity LHC. Here you can see me while I'm testing some models for the upgrade of the tracker. And before concluding, I just want to briefly mention science communication that takes a significant time, a significant part of my time. I enjoy doing these at very different level, like general audience. Here is a physics briefing on my latest result in CMS, where you can see LFUV became a Napolitan ice cream. I was part of the delegation that visited the Congress asking for appropriations in 2024 for the implementation of the P5 report. And then with students, here it is with high school and even with undergraduate students. This is a program I created last year to lead undergraduate students to perform a summer research experience at CERN or PSI experiments. And then with kids. It's about 3 years that I'm the PI of 2 projects with Walt Disney Company to teach my research and to teach kids about my research. I think many of you probably recognize this. It's Uncle Scrooge Money Bin, and you can see there is a muon detector because you can be creative elsewhere. So this is basically a story that was published in Topolino in Italy. So I use it as a reference to be as accurate as possible, a study for a muography of Santa Maria del Fiore, the beautiful dome. And based on this, we did this nice story on Topolino. And as the PI of this project, there were other couple of stories Paris about Mars exploration and gravitational waves with other colleagues, and we taught many beautiful things. This became an educational approach, and indeed some schools in Zurich and with the consulate, Italian consulate in Zurich, one story became part of the science program of the school, and last year I had so much fun in training teachers and then teaching kids about these topics. And so a new project, I have a grant, and as part of this grant, there is a new project where I will continue these efforts, just including even augmented realities with phone app applications. And I'm moving to my conclusions. I hope I managed to tell you how sometimes you have already the right telescope to observe a new physics comet. You just need to be creative and do it, because you can really do it. I want to thank all the amazing people I worked with, because particle physics is by definition a collaborative effort, and all the amazing people at ETH Zurich, University of Oxford, Fermilab, my supervisors, Gunther Dissertori, and Fermilab people, Joel Butler. But it means a lot to me to thank my amazing PhD supervisor, Professor Ian Shipsey, who sadly passed away 2 weeks ago, and I'm sure I will not be here today without his amazing support in the past years. And with this, I'm done. Thanks, and I'm open for questions.
Thank you very much, Luigi. So let's start with the questions. Elena, Alessandro, do you want to start, or do you want me to start?
Yeah, I can start. So thank you for your explanatory presentation. And if you can go to slide 30. So you discussed the method to use the beta meson and how to be competitive.
Mm-hmm.
What's your contribution on this idea, and was this method already used by other groups or experiments before?
Yeah, so the thing is that the ratio strategy has been used in other contests and also in this contest. So the idea of using a ratio for precision measurements, it has been used in other contests as well. The key point here was, of course, the idea to make the measurement possible at CMS, because, I mean, I can show you that there is, for instance, if I go back here, yeah, I can show you here that at CMS, we had also another result that was done considering the hadron decays of the tau lepton, rather than having a muon decay, and so having just muons and neutrinos in the final state, an hadron decay for the tau. And you can see that it was interesting and good, but the best one here, it was for sure coming from the muon decay, the one I worked on. So this is just to say that, again, it was possible to have other ideas and even work on the top of these, but still the key here was to have this special final state. I hope I addressed your question.
Thank you. Thank you. Yes, it is addressed.
Yeah, maybe I may follow up on that if you don't mind, Alessandro.
Go ahead.
Yeah, actually, my question was very similar, because the ratio method to eliminate the systematics practically is widely used in particle physics, nuclear physics. So if you want to get rid of systematics, you are looking for ratio, and then you say, okay, but in general, you pay a price for this. Anyhow, I was trying to understand, so to confirm what was my impression is that it's not the ratio method, the key contribution here is to look for a specific final state to reach this sensitivity. And you confirm this, if I understood correctly.
Yes. And I also want to stress out the importance of the B sub C, because this is a unique opportunity. You know, as I said, also, there are other experiments. We know that there is Bell 2 in Japan that is also a B factory, right? But right now, they cannot produce this meson because they don't reach the threshold. This is also a relatively young B sub C meson, was discovered at the CDF around the end of the 90s. So, you know, we're still better characterizing this special meson, but it's a unique opportunity just for us. So key was also to, you know, decide to work on this specific B sub C meson rather than like, I don't know, other B0 mesons that are largely used nowadays. Indeed, there is just another measurement from this.
And what about your contribution in the other measurement also that it was a slide 20, yes.
Yeah, this one, yes. So
the ZZ, the decay of H, even if I understood that the branching ratio of this decay is very small, is 7%, 8% from the first slide, one of the first slide you presented. But nevertheless, you said, I'm going to use this. And is this idea developed by yourself or in a team? Also, this is, I want to understand what is your contribution.
Sure. Yeah, that's a good question. Thanks for asking, because it's true that in particle physics, we always, in, you know, high energy physics, we always work in groups. And indeed, for all this analysis, there was a group. But so this was the main topic of my PhD thesis. So I worked on the decay of the Higgs to ZZ and then 2L to nu, as you may see here. That was the first initial work I did. That was really tough because when you have neutrinos, as you know, in our detectors, it's really hard we don't see them. So you infer them as missing transverse energy. So I worked on these, and this is a plot from my thesis, my work. And then in a group of 40 people, then I worked on these results on the one from the other channel, and I had to do the combination of this channel to produce the final result. So the 4 lepton and the 2L to nu. So for this measurement, in a group of 40 people, I was the main data analyst working on this, even for the documentation, and that was needed for this. If you want, I can expand a bit. I have some backup slides.
1 minute left.
I don't know if I have time, unfortunately.
Okay.
And I want to leave some time also to Alessandro, if he has a question. So I wanted to know a little bit also more about your contribution in the hardware, because also in the hardware, you jumped from electromagnetic calorimeter to tracking. So it's a quite complex detectors. But unfortunately, we have 8 time. We have to be on time. And I want to leave Alessandro the opportunity to ask his question.
I had a much different, very broad question, which is the following. If you had a magic wand and a lot of money, what accelerator and what detector would you advise to do to maximize the physics output? Not much to eliminate the chance of having any, but where do you think the sector should go?
Okay, then I myself, I'm thinking a lot about this question recently, because there are 2 projects that are really interesting to me. One is the Future Circular Collider. As Italian, European, I strongly support this, and I think this is the way to go, because what we really need to do is to finish the study of the Higgs boson, and for sure FCCEE is the way to better characterize. A lot of these measurements that I showed you here can be done with the high precision at the FCCEE. So I truly support, and also would be great to have these Europe to continue our leadership in the field. At the same time, I'm really interested as a physicist on the developments for the muon collider that is taking place in the United States. It's true, there are still many challenges to be addressed because, there will be a large occupancy. We will have all these decays of muons. It's still not 100% clear if we can really we have the right technology to make this possible. But at the same time, I think we are just postponing the problem because, after the FCC, what will be next? We will be building a tunnel of 500 kilometers. So with the muon collider, you can, in principle, obtain similar results to FCC-HH, which requires a tunnel of 100 kilometers, with a smaller tunnel and a more feasible tunnel. So I think this will come anyway next. So I feel a bit like that we are just postponing the challenge to the next century. So I think as a physicist, to reply to your question, I'm way more interested in the muon collider because I see the challenge. As you may have seen, all the research I did was often considered not possible. So following this line, I think the muon collider is more interesting to me, but I see more solid the future circular collider for sure continuing the Higgs research program in the short term. I don't know if I replied to your question.
Absolutely, and it's could be a long debate. So I appreciate the quick response. Thank you. Nice presentation.
Okay, thank you very much, Luigi. And let's move to the last candidate now, Dr. Antonella Palmese. Antonella is assistant professor at the Carnegie Mellon University here in the US. And she will tell us about gravitational waves as a new cosmological probes. Antonella, probe, actually. Antonella, stage is yours.
Okay. Hi, everyone. Thank you so much for the opportunity to tell you about a big part of my research, but this is not everything that I do. And so today I'll focus on gravitational waves as a new cosmological probe, and new in the sense that gravitational waves were detected for the first time in 2015. And so this is the current landscape in which we live. So this is all of the gravitational wave detections that we had up to the end of the third observing run. So 3 LIGO Virgo Kaga observing runs were completed, or 1 or 2 and 3. And the fourth one is currently ongoing. So I'll show you one preliminary result for that, but most of the results from the hundreds of new detections that we have will come out in the next years. So this is what we had up to the beginning of 2004. Here you have on the y-axis the mass of the component in the binaries that have been detected so far in units of solar masses. And then other than these 2 components, you see a third component in each of these detections that tells you what was the mass of the remnant objects that was formed from the merger of these binaries. And most of those are black holes, as you see there in blue, but you also see a few neutron stars that are shown in orange. So this is what we'll work on. So let me start with gravitational wave detection. So these are ripples that propagate in the fabric of space-time and that are observed by current generation gravitational wave detectors as a dimensionless change in the lengths as the gravitational waves pass through the detectors and perturb the space-time. And the gravitational wave signal that is detected from those looks like this waveform that you see in black here in the video as 2 compact objects, so 2 black holes, 2 neutron stars, in spiral around each other and merge. Now, gravitational wave detectors are spread around the world so that they are able to, we say, hear the signal and triangulate it in the sky. And so LIGO Virgo Kaga are able to provide us with this kind of maps in the sky that tells us where the compact binary object occurred. And then we can use telescopes. This is what I do. I use telescopes to follow up these regions in the sky and try to look for the light that was emitted from the merger of these compact objects. So we are, with my group, we're part of a big network of telescopes, both ground-based and space-based, looking for this kind of signals that we call electromagnetic counterparts to gravitational wave events. And then if we find those counterparts, we're able to combine the gravitational wave and electromagnetic wave data in order to make some what we call multi-messenger analysis. So on the electromagnetic side, what I'm focusing on is the dark energy camera. So this is still one of the best, if not the best instrument currently available for gravitational wave follow-up. One of the main reasons being it has a quite large field of view in the sky. You can see here how its size compares to the size of the moon. And so that lets us cover these regions in the sky, these gravitational wave maps, quite quickly, looking for these faint and fast counterparts to gravitational wave events. Dark energy camera, DCAM, was built at Fermilab for the Dark Energy Survey. That was a US Department of Energy funded program that imaged about 5,000 square degrees of the sky over this tank-shaped footprint that you see here. And so that was data for about 300 million galaxies in optical to near infrared filters that we call GRI, C, and Y filters. And I'll very briefly mention also the Dark Energy Spectroscopic Instrument, DESI, which is another galaxy survey currently ongoing and has already created actually the largest 3D map of the universe. So the main quantity we want to measure with this kind of surveys is the redshift of galaxies. Think of it as a Doppler shift for electromagnetic waves. The idea being that if a galaxy is moving away from us, its spectral energy distribution, shown here in black, will be shifted towards the redder wavelength. So that's why the name redshift. And so with the Dark Energy Survey, we use the filters information, and you can see how the light changes across the filters for different redshifts to infer the redshift of galaxies. And we can do an even better job with something like DESI because we have spectra, so the entire spectral energy distribution information to measure an even more precise and accurate redshift for each of our galaxies. So the redshift, I told you, tells us about the velocity with which galaxies are receding from us, so that can tell us about the rate of expansion of the universe. More specifically, the rate of expansion of the universe close to today, which is the Hubble constant h0. And one main reason why this is interesting is because of the Hubble tension. This is one of the biggest problems in modern cosmology. It's an observed 4 to 6 sigma discrepancy between measurements of this variable between early time universe measurements, so mostly those coming from the cosmic microwave background, and late time universe measurements, so closer to the universe of today, mostly coming from one specific type of measurement from supernova type 1a. So one is closer to values of h0 of 67 kilometers per second per megaparsecs, and the other one is around 73 kilometers per second per megaparsecs. So the question is the discrepancy arising from some systematic uncertainty, maybe that we have not properly taken into account in one or the other probe, or is there new physics, perhaps that we need to take into account when we make, for example, the h0 measurement from the cosmic microwave background that is really tied to a specific cosmological model. So if we're looking for an independent measurement that could tell us where the h0 value, true value actually lies, if we want that from late time universe, like the gravitational waves that we saw earlier, then ideally we want that to be independent of all the possible sets of systematic uncertainties that might affect the other late time universe measurement, which is the one from the supernova type 1a. And so gravitational waves do give us that opportunity because we can measure the luminosity distance, unlike what we do with supernovae. We can measure it directly from the gravitational wave data. So the in spiral phase of the binary, the amplitude of that really depends on this luminosity distance of the binary. So we can measure that from gravitational waves. And then if we're able to identify an electromagnetic counterpart and pinpoint the host galaxy, then we can get the redshift. And so we can start populating this, what we call Hubble diagram with various events and measure this distance redshift relation, which is in turn sensitive to the Hubble constant, at least at the lowest redshifts. So there's different ways we can make standard siren analysis. I will focus on the first two, which are the truly multi-messenger ones. So the first one is the most straightforward. It's a bright standard siren method in which we have the redshift information coming from one unique host galaxy because we have been able to identify the electromagnetic counterpart. And this is what we expect mostly for binary neutron-star mergers. We expect them to emit light. On the other hand, when we don't have any electromagnetic emission, mostly the case for binary black hole mergers, you have two black holes that merge, you don't expect to see any light from that. And so in that case, what we do is we take into account all of the potential host galaxies within a statistical framework, all of the potential host galaxies that fall within that sky map, the gravitational wave sky map that I mentioned earlier. And so in that case, the redshift is coming from the redshift distribution of the galaxies along the line of sight for each gravitational wave event. So let's focus on the first one. So what is the actual signal that we're looking for here in electromagnetic waves? If you have two neutron stars that are colliding, the expectation is that you might have a relativistic jet that is launched that we can detect in the gamma rays. And this is what you see here in the video in magenta. you might have a kilonova signal that is more isotropic that you see here in violet and white that we can detect all the way from UV potentially to infrared. And then also an afterglow that is coming from the interaction of that jet with the circumstellar material that we might be able to detect all the way from X-rays to radio.
5 minutes left. 5 minutes left.
Thank you. So all of these were actually detected for GW170817, an event, very famous event from 2017. And I was part of the team that was able to discover the kilonova signal. As you can see here, it's coming off. And so it was exactly the fact that we were able to identify the kilonova that let us pinpoint the exact host galaxy, enabling the first measurement of the standard siren. But in addition to using data from the host galaxy, we can also use data from that transient event to constrain the viewing angle of the binary. So as you saw, like if you're looking at the jet, if you're seeing a jet and perhaps the also the afterglow emission, it means that you're probably close to on axis with the binary. And so you can infer something about the orientation of the binary. And this is important because there is this degeneracy from gravitational wave data alone between the luminosity distance of the binary and the viewing angle. And this is the posterior, to be posterior in blue. But if we add this extra information from the afterglow that we used data all the way to 3.5 years after the gravitational wave event, we're able to constrain this 2D parameter space much better to this gray contour that you see here. So that means a much better, much more precise measurement of the luminosity distance, and in turn, a much better constraint also on the Hubble constant. So the final posterior that we got is given here in black, posterior on the Hubble constant. And you can compare that, which has about 7% precision, with the measurement that we got in 2017 that is given by this dark orange curve, which had about a 14% precision. We also took into account peculiar velocities from the host galaxy and the group, which can actually also be used to probe gravity in the future, as we showed in another work. So our result actually lies close to the supernova value of the Hubble constant, but is still consistent within 2 sigma of the cosmic microwave background measurement. So more measurements will be needed in order to discern between these 2 values. Now let me move on to the dark standard siren case. So what we did in this other case is we started with the gravitational wave events that had a sky map falling within the dark energy survey footprint that you see again here. So we've made, I led the analysis that provided the first measurement of the Hubble constant using a binary black hole. Then we added another one that was detected 2 years later. And then we were able to add even more events from the third LIGO Virgo Kagra observing run using also data beyond DES, including the DESI imaging observations. And so we combined these events that you see here in different colors to obtain a dark standard siren posterior that you see here in blue. And by combining that with the event GW170817, we were able to, that I showed you earlier, we were able to improve our constraint by about 30%. So we're getting more and more precise as we move forward with these measurements. So the last thing I want to mention is that I said so far we're looking for counterparts from binary neutral submergers. Most binary black holes will not have an electromagnetic counterpart unless we believe that these binary black holes merge in a gaseous environments, such as the disk of an active galactic nucleus, which is basically a massive black hole in the center of a galaxy that is accreting material. And so in this case, you might be able to see some electromagnetic counterpart. The problem is that these sources, the AGNs, active galactic nuclei, are actually variable sources. So we're looking for something that varies on top of something that varies, which is very complicated. But we came up with this Bayesian formalism back in 2021, showing how actually after we have a population of flares and a population of binary black hole mergers, that we can actually make this association between the 2 objects. And this association could be possible next year, as well as a hybrid standard siren measurement in this case. So we use the same formalism not only to establish the association between binary black hole mergers and AGN flares, but also to constrain the Hubble constant and in the future dark energy equation of state and the content of matter in the universe. So we are engaging in this follow-up with the US NSF-funded survey with the dark energy camera. We're following up events of all kinds from the current observing run, and this is our team, mostly at CMU, that is leading this effort. We have this rapid GPU-enabled and AI tools pipeline that let us discover very quickly transients and publicly report all of these discoveries so that everyone else can follow them up with their own telescopes. So far, we have found one candidate electromagnetic counterpart from this event from last year, from a binary black hole. And you see here the flux as a function of time for this event that we detected. So I'll just conclude by saying that what we'll need to understand the Hubble tension is a 2% precision measurement on the Hubble constant, something that we'll reach with about a dozen bright standard siren and a few hundreds dark standard sirens. But there's a lot more that we can learn by combining gravitational wave and electromagnetic observations, which goes on to the origin of black holes, which is also something that I study, the formation of heavy elements in the kilonova ejecta, nuclear physics from neutron stars, and dark energy. And so I think my main goal right now is to find the next electromagnetic counterpart to a gravitational wave event and enable all of these studies with that. And I'll stop here and take questions.
Thank you very much, Antonella. Very nice presentation. And we'll move on now with the question. Elena, do you want to start? It's your field, this one.
Yes. So thank you for the very interesting presentation. So I have two questions. The first one is, what's your contribution on the dark sirens method and surveys? And the second question is, your primary, what do your primary results indicate about the Hubble constant tension that is given by systematic effect or a hint for new physics?
Yeah, okay, thank you for those questions. So on the dark siren method, so the idea of the dark siren actually was first put forward in the 80s. So the first idea of standard siren was, we believe, we're not sure that we'll actually see an electromagnetic counterpart. That wasn't clear back then. And so people thought, well, Bernard Schutz wrote this paper in Nature paper where he showed that you should use galaxies. You should be able to use galaxies and their redshift to make a standard siren measurement. And so that was the first idea. My contribution was mostly on the data analysis side, application of this method with real data for the first time for a binary black hole merger. And, so it was a development of the pipeline to make that measurement possible. And then on the systematic side, especially working on systematics that we expect from photometric redshifts. I would say that's been my main contribution, but moving forward also to other types of systematic uncertainties that we have, we're still learning from because it's still a new method. And so the application to these large sky surveys, DES and the DESI legacy survey, that was my main contribution so far. And then in terms of what my results find, so the level of precision, again, isn't enough yet to tell us something conclusive, but it seems like we're leaning towards the higher values. So that would be closer to other late time universe measurements. And so if that is confirmed, that would mean that perhaps there could be some new physics that we need to be taken into account, some sort of like early dark energy maybe that has been proposed to be able to resolve the tension. So that's also what I hope. That would be the most interesting answer.
Thank you.
Alessandro? Or I can ask my question if you want.
Sorry, I should unmute before starting to ask the question. So you talked a lot about the challenges in the science. Can you address a bit the challenges in technology? In other words, do you have the right detectors? Do you have the right systems? How hard is it to acquire the data and then process it?
Yeah, that's a great question. I would say that at the moment, I don't know that there is a technological problem, at least on the electromagnetic follow-up side. I think we do have all the type of detectors that we would need. Is more of a question of, are we actually using all of these facilities that exist in a clever way and in an optimized way? And that is actually not the case. It's also like a question of more, I would say, on the software side. Maybe that's more, also what I work on. Creating these pipelines that are able to analyze the data as fast as possible is really hard, also because rely on all the sorts of software that we use in astrophysics in order, for example, to do the source extraction in our images that are, for example, not GPU enabled. So they're very slow, and they're too slow when we're looking for something like a kilonova that really explodes and evolves and fades away in a matter of a day. And so probably we only have, a few hours that we can observe that object in the sky before it sets and the counterpart fades away. So I would say perhaps now the main challenges are on the data analysis, on the pipeline side more than on the detector side.
Thank you.
And indeed, my question, okay, I had a couple of questions. One you already answered. What is your contribution to the results that you have shown? And the other one is a follow-up of your point about the software. So the tools that you use to analyze your data. If you go to your slide 14, for instance, in which you should, I think it was 14. Yes, this one. So you reduced the width of your curve, the orange to the blue, right, to the black, quite consistently. Now, my question is, what is the system? You use a certain, you have your data, and then I can imagine the way you use your data, you analyze your data. Then you have the model, right? In a certain sense, you have to fit then your model, or you have to check how your hypothesis is comply with the model. Sorry, I have to stop my phone. And you have a systematic uncertainties in your projection. So what is the systematic uncertainties in this curve? Is it folding in the width?
Yes, somewhat it is. So one of the things that, okay, there could be different sources of systematics. The ones that we have taken into account, they are folded in. So there's two main systematics that we consider. So one is the peculiar velocity that I mentioned. So you have basically the redshift that we observe from a galaxy is not fully coming from the expansion of the universe, which is what we plug into that distance redshift relation, but there is a contribution coming just from motion due to the local dynamics of galaxies, and that's really hard to measure. So that's something that we take into account. So actually, the measurement that we start from, it's not the orange-blue curve, is this lighter orange curve, which has a larger uncertainty because of this reason. And then the second systematics that we take into account, is about the jet structure. So the afterglow light curve, so the flux is a function of time, will really depend on the structure of this jet. Does the energy as a function of angle follow a specific function like a Gaussian, or is a top hat? And that will really change how that light curve looks. And so that's something that is folded in the models that we marginalize over these different kinds of models and different kinds of jet structures. So that uncertainty is taken into account there. And so, in fact, if you compare this to, there have been a couple of other works trying to do something similar, and some of them have a smaller uncertainty because this uncertainty isn't folded in. But what we haven't taken into account, for example, is that there is different modelings that you can do even for different jet structures. And
yeah, in fact, sorry, I understand your point. So if you go, for instance, to slide 6, just to close the discussion, because I think that we are already this one of the Hubble constant. So is this a real puzzle, or is just due to the different way to treat some systematics that some unknown? I
that's
don't know.
yeah.
Maybe you cannot answer this question, but when I saw this difference, it came to my mind, this is something systematic, so that in the early time, when you do some measurement, you don't consider, while when you do different measurement for the late time, so some systematics that doesn't enter. I don't know how to, it's not my field, but try to understand if it's a real puzzle or not, or it's just the way to analyze the data.
Yeah, it's a very big debate. I think the
Okay.
question about systematics applies more to this specific measurement. So as you can see, there's different other types of supernovae from the tip of the red giant branch. Basically, you need to calibrate your distance to the supernovae using other distance indicators. And that's probably where most of the systematics in the late time universe will come from, because they're the same supernovae. But the calibrators are different. And the fact that this other calibrator finds measurements that are in between what the Cepheid anchored measurement and the cosmic microwave background find leads people to believe that maybe this tension isn't really there. But there is a lot of debate, also including new data from the James Webb Space Telescope, that it's unclear to me whether this is a problem or not. But yeah, I think the CMB measurements are very solid, but these assume a flat lambda CDM scenario, so specific cosmological model that does include, as I mentioned earlier, like early dark energy. And so if that cosmological model changes, then this value shifts. So, but that would be interesting to know, because that means that the cosmological model that we typically assume is not actually a true one.
Yeah. Okay, I think that we have to close here. We actually ran out of time a little bit late. First of all, I want to thank all the three candidates here. Excellent presentations, and I like very much your enthusiasm, the enthusiasm that you showed in presenting your research. Really, very, it's really important to do this work in this way. So I don't know if Enrica or Cinzia, what is the closeout? I think that Cinzia has to say something. I think that for my part, thank you very much to everybody. And I hope to meet you in person in November in DC.
Thank you, Patrizia. It's now my turn. I can only echo your remarks about the wonderful set of presentations. It has been most enjoyable for me to listen to the three talks. This is our most recent Young Investigator Awards, and we are very grateful to the INFN for sponsoring this award, which is now in its third edition. So it's always a pleasure, because the community here is so strong, right? The physics is an area of excellence historically for Italy, and the community in North America reflects and represents that same strength as it is implemented with the flavor that can only take place because we are in North America. It's good to see the many areas of collaborations, and particularly the great enthusiasm from you, the three finalists. I wish to thank the chair, Patrizia, who has done a wonderful job in her second year doing this, Alessandro this year, and Elena as jury members that have allowed for a robust process in what I'm sure was a hard work in selecting the set of finalists. And I look forward to meeting you in person next month in Washington, D.C. And then we will know who the winner is. But as far as I'm concerned, you have already won. That is an extremely valuable trajectory of career that you have shared with us today. With this, this symposium is coming to a close. Thank you very much for your time and for attending.
Thank you. Bye-bye.
Bye-bye.